Quiet, Jacob.
Oh! Now get it back on.
Greetings and welcome, friends. We're taking a look again at roots and zeros when we're exploring polynomial functions. All right, so yesterday we talked about, what was that? The fundamental theorem of algebra and its corollary, as well as the complex conjugates theorem. Am I right? I'm right. So today we're looking at this additional piece. This is called Descartes', and that's the last time I'm going to try to say that in French, rule of signs. All right? And this is René Descartes, Rainy Descartes, the dude that said, I think, therefore I am. Right? So, Descartes' rule of signs. There we go. So, he said, and he must have just been really looking at a lot of polynomial functions one day to figure this out. He said, if p of x is a polynomial function, okay, I can imagine that, whose terms are arranged in descending powers of the variable, that's just called standard form, by the way, he has two facts that conclude. Whoa, here we are. He said, one, that the number of positive real zeros, all right, positive real zero, that would be like if it had an x-intercept of positive 5, positive 2, right? Positive 7. Those are positive real zeros, okay? He says that the number of positive real zeros of p of x is the same as the number of changes in sign of the coefficients of the terms, all right? So if our terms are going like positive, negative, negative, positive, right? I count the number of changes in sign, not the number of negatives or positive, but the number of changes in sign, and that will be the same as the number of positive real zeros. And then he has this other stipulation. He says, or is less than this by an even number. And regarding zeros and polynomials, which ones occurred in pairs? Imaginary ones. So this last little stipulation is regarding the possibility of imaginary zeros, okay? So he's saying that, well, if there's any imaginary ones, there would always be at least 2 of them or 4 of them, right? Or an even number of them. So it could be less than this by an even number. Next fact, he says, the number of negative real zeros. What do I mean by negative real zeros? Well, that, of course, is referring to, like if it crosses at -1 or -7, -23, right? Those are negative real zeros, right? And he says that that's the same as the number of sign changes of the coefficients of the terms of p of negative x, not the original p of x, but p of negative x, right? So you count those sign changes, you know how many negative real zeros you have, all right? Or is less than this by an even number. So once again, the possibilities of, imaginary roots, right? They come in pairs, basically. That's the idea. So let's do an example of this. All right, exemple, Descartes. Let's see, state the number of positive, negative, and imaginary, I'm going to add, roots, or zeros. Should I say zeros? Doesn't matter, zeros. I'll say zeros then. Zeros for the following. All right, suppose I've got, I'll call it f of x for fun. F is for friends. There we go. Down here in the deep blue sea, I'm going to write this polynomial out as 4x to the 5th plus 3x to the 4th minus 2x cubed plus 5x squared minus 6x plus 1. All right? Now, what I'm going to do, I'm going to leave some space because I'm going to have to do like maybe 2 rows of calculations here. But I'm going to make a chart. All right? This little chart. It's going to be great. And I'm going to have positive zeros, negative zeros, and imaginary zeros. All right? And I'm going to have the possible combinations. Now, first of all, how many zeros does this have? Definitely 5. Has to be Has to be 5. Exactly 5. Not at least 1, not less than 5. Exactly 5. All right? So I know that the number of positive plus the number of negative plus the number of imaginary has to all add up to 5, right? Every time, no matter what. So all possible combinations. So now let's try to find them. Well, he said I can find the number of positive ones by counting the sign changes in my function. So let's do that. So here we go. No sign change. It went from positive to positive. Ready? Oh, there's one sign change, right? It went from positive to negative. Now it went from negative to positive. That's a total of 2 sign changes. Positive to negative, that's another sign change. That's 3 total. And negative to positive, that is 4 total sign changes. So when I'm filling out this chart, I know I have 4 possible positive ones, or less than that by an even number. Okay? Now question, could, theoretically, I haven't done any more work yet, but could this be a possible outcome?
Yeah.
It adds to 5.
No, there has to be 2 imaginary.
Yeah, because there can never be 1 imaginary, right? Because they get lonely. So they always come 2 by 2. All right, excellent, excellent. So let's see, now if I want to calculate the number of possible negative ones, what do I have to know? I have to know what I get when I plug in negative x into the function. So let's do that. So I'm going to calculate what is f of negative x, or f of the opposite of x is technically more appropriate, because technically if x was originally negative, the opposite of it would be positive. So calling it negative x can be not technically mathematically accurate. So I'm going to, how do I calculate f of the opposite of x? Yeah, plug in the negative x for all of these, right? And you might have to remember your properties of exponents. It's gonna be good. Here we go, plus, I hope I don't run out of room, negative x squared minus 6 times negative x plus 1. Whew! All right, so let's simplify this and then I'll count the sign changes. So f of, negative x is equal to, now question, a negative number raised to an odd exponent is still negative. So this I could simplify to be negative 4x to the 5th. Right? You guys remember them there rules? Descartes' rules of signs. Here we are. Negative raised to an even will be positive. So this is positive multiplied by positive 3, still positive. So I can just simplify that to be positive 3x to the 4th. Okay, all right. Negative to an odd is negative. Multiplied by a negative is going to be positive 2x cubed. Right, so I just have to go through each term, be very cautious with my signs. So let's see, negative raised to an even is positive. Positive times an already positive is still positive. So that simplifies just 5x squared. Negative times a negative is positive, and positive 1 doesn't change. So let's count these sign changes. Negative to positive, that's 1. And then it's going to stay 1 for the rest of its life. No birthdays. 1. So, so I could have 4, 1, and in this case, how many imaginary could I have? How do I know it's going to be 0? Why can't it be 2? Because it has to add to 5. All right, so the trick is I'm just going to pick combinations that add to 5, but still hold true with the number of imaginaries. So this is a possible outcome. I also could have had, I said I could have reduced this by an even number. So this could be 2, 1, and how many imaginaries would there be in that case? 2. All right. What if I reduced this by an even number? That doesn't even make any sense. Okay, so I just want to point that out, that this is now telling me what kinds of roots I have. Not entirely as accurate as a discriminant in the case of a quadratic, but it helps me narrow it down. So for instance, if I already found a negative root, and I'm kind of doing my guess and checking there, Hank, I wouldn't keep looking for roots in the negatives. I would just be like, well, I'm going to start checking zeros and positives, right? And that's what I would do. Just as a quick, brief example of this, let's say it was the same kind of problem and I did a bunch of work and this is what my chart looked like. Let's practice filling out a chart for a different outcome because sometimes these can be tricky. What if I had 3 and 4 and 0? What would the degree of this polynomial have been? Right, so this is a 7th degree polynomial, guaranteed. So suppose this was the result, and now I've got to figure out all combinations. So 3, 4, 0 is a possible combination for the times when I had no imaginary, when I have no imagination. Or I could reduce this by an even number. So I also could have 1, 4, and what would go here this time? 2, since I want them to add to 7 still. Or I could have had 3, 2, and well, it's still got to add to 7 because we agreed that p of x is some x to the 7th thing. So how many would be here? Oh wait, 2. Yeah, you're right. I thought I still wrote the 1 there. Man, you guys are all just like, Mr. Waddy, it does add to 7. Don't know what you're talking about. Let's see, and I think there's more possible combinations. Let's see, I could have also had a 1, a 2, and a 4. That's the one I was thinking about earlier. Okay, have I hit all possible combinations? Well, this one still can be reduced by an even number. Maybe there's no negatives. And I'd have to consider 0 with these 2 possible outcomes. So I could try 3 with a 0, 1 with a 0. 3, 0, and 4, or 1, 0, and 6, right? So the even numbers come always in pairs, and the others we just have to try kind of all possible combinations. So see how I had 2 outcomes for this, and I had technically 3 possible outcomes for that. So I mixed and matched all of them until I got the total number of 6 outcomes, which is kind of the number of ways that could work out. So I just want to point out that's a possibility right there. You get that down? Last example. Exemple! Here we are. Okay, here's the last kind of problem. This one's actually, you already technically know how to do this if you knew how to do the complex conjugates thing. This is what it would say. It says, write a polynomial function of least degree whose zeros include, well, I guess I'll add this other piece, with integral coefficients. So don't make anything crazy. Whose zeros include. Include the following. What if it has 7? Actually, I'll write those in yellow. And blank. Let's see, blank. And I'll have 7 and 3 plus 2i. So this is kind of like on yesterday's quest when we were talking about finding the depressed polynomial that had those roots. Well, if 7 is a root, what would a factor have been? X minus 7 would give me a positive 7 as a 0, right, or a root, right? So if 3 plus 2i is a 0, then a factor must have been x minus that 3 plus 2i. And then wait a minute. Yeah, if I have 3 plus 2i, that one's imaginary. That means 3 minus 2i had to be as well because of the complex conjugates theorem. And if 3 minus 2i is a 0, then x minus, in parentheses, 3 minus 2i would be a factor. So this polynomial, right, would have all of these as its zeros, all right? And I could have had a polynomial with like an x plus 1 and an x minus 42 and blah, blah, blah. But they wanted the polynomial of least degree. So least degree means it's only going to have the degree that has the bare minimum number of zeros that we knew about. So this is going to be a third degree polynomial. I don't want any extras, right? So if I want to calculate what this polynomial is, that's going to take some space. I'm just going to have to like massively distribute this. So I'm going to simplify these first. I'll distribute this little minus sign to that and that, and that and that. And I'd have x minus 3 minus 2i and x minus 3 plus 2i, because double negative, of course, the negative times a negative 2i is positive 2i. Now, when having three things multiplied, I can't distribute this and this and this and then this and this and this. And like, I can't triple distribute all at once. I'm going to distribute just these two first, okay? And then when I get my answer, I'll distribute the x minus 7 into it, okay? So you have to do it kind of piecemeal like that, just so you're aware. So x minus 7 times, well, let's see, let's distribute this. X times x is x squared. X times negative 3 is negative 3x. X times 2i is, what, guys, it's my favorite. It's Twix. I love it. Again, it's back. Negative 3 times x is negative 3x. Negative 3 times negative 3 is positive 9. Negative 3 times 2i is minus 6i. And one more thing to distribute this guy to all of them. Negative Twix. Oh, they stole my Twix again. Negative 2i times negative 3 is positive 6i. And negative 2i times positive 2i is going to be negative 4i squared. Whew. I don't know about you guys. Were you able to fit that all in one line? I hope so. Okay. So, let's simplify this guy. And right, those guys cancel out. Negative 3x can combine with its buddy. And 9 can combine with negative 4i squared. It's the same as negative 4 times negative 1. Same as positive 4, right? Yeah, yep. So I'll have x squared minus 6x plus 13. And now I just got to distribute again. And I'm almost there, friends. Now I'll distribute. And right? You got it. You got it.
You got it, dude.
You got it, dude. X cubed minus 6x squared plus 13x, and then distribute the negative 7. So minus 7x squared plus a 42x, and minus 70 plus 21, 91. And I can combine some like terms there, and I'm done. So this way I can actually find polynomials with given x-intercepts. So say like you were doing your little catapult project for physics class or whatever, and you knew where your object started and you knew where it landed, and you wanted to find a possible polynomial that had that. You could kind of use this to get started with a little bit anyway. A little bit. Let's see. I just combined that wrong, guys. That's not 36x. Negative 6x squared and negative 7x squared is going to be negative 13x squared. Silly me. And then 13 and positive 42 combined to be 55x minus 91. So that's how I can find a polynomial function that had those particular zeros. Not bad. So that was Descartes, and then a little extra facts right there. Thanks for watching, Internet friends. Bye-bye.